Though these Heidelberg man people lived here 600,000 years ago, they lived on the observatory gravels. We have no record that they actually had their own observatory or what their astronomy was. So unfortunately we can't tell you any more about them, except that people have been here for a very long time. So jumping ahead quite a lot to the early history of astronomy in Cambridge, it's been astronomy here since medieval times. Which we won't go through. And astronomy started with significant observatories in several of the colleges. There were two that are much talked about. This one, which was on top of the front gate at Trinity College, and is talked about a great deal, and there's lots of pictures of it around. It was clearly endowed with lots of nice instrumentation, which still exists in museums. But there's no record of it ever being used for anything except for launching fireworks displays. And so far as we're aware, there was no astronomy ever done in the Trinity Observatory, and so they pulled it down and put a clock there instead. This one, however, is much more significant. This is in St. John's College, and was a very major observatory for over a century, and in fact continued in parallel with the observatory here, and produced a very great deal of substantial published science, which I won't go into here because there is a superb website. St. John's College has a really good website for the history of astronomy in St. John's, and in fact it runs up to overlap with us because it's also the repository for Fred Hoyle's papers. And so later on he picks it up. But anyway, the background, the real background to why there is astronomy in Cambridge was started, of course, with Newton. Everything starts with Newton. And following on from him, Cambridge set up the Tripos exams. So if you wanted a degree from the mid-18th century on from Cambridge, you had to pass the Tripos exam. And the Tripos exam was a Newtonian mathematics exam. And it was written in Newtonian style mathematics, fluxions as they were called. It's ghastly stuff if you've ever seen it. And so quite soon afterwards, the mathematicians of the time tried to change and modernize the mathematics by adopting French mathematics, which is our modern style. And so somehow or other, they decided that part of this attempt to modernize the mathematics curriculum involved becoming focused on building an observatory. So they tried in the late 18th century to do something about this and failed. But then the real founders of the observatory came into the picture. And so this person who's barely known in the astronomical community at all, George Peacock. George Peacock was essentially single-handedly the founder of astronomy in our observatory in Cambridge. No one's ever heard of him, which is ridiculous. We should have his picture blazoned in great state in our observatory. So the dates here are the dates these people came up as undergraduates. He later became a mathematician, a Lowndean professor, Dean of Ely, and translated the French mathematics books just at the end of the Napoleonic Wars, became a maths examiner and changed the curriculum. One of his colleagues was John Herschel, son of William Herschel, a great astronomer, and they formed a band of three with the other Charles Babbage, later also a Lucasian, famous as father of the computing engine. And he revised, when he became Lucasian, he revised the maths tripos firmly. So already within a decade of their ambitions, these people had achieved their primary aim of modernising mathematics in Cambridge. So that was triumph number one for the observatory. They got a second triumph, which is here. I'll leave you to do the Latin translations yourselves, I'm sure you all can. Is that already by 1817, just a decade after these people appeared as undergraduates, they'd managed to build up enough support among all of the physics, maths, astronomy professors to get the university to support the endowment, or not endowment, the founding of an observatory. And so they were approved. They set up a little committee. They were told to go and raise the money and build the building. The building, of course, as is typical in these things, came over 100% over budget. And after very many grumbles and complaints, the university eventually paid the bill. But this was all happening at a time of great change, both in Cambridge and in the British system and in Europe. But they built this, the Mead building, which is the original building over there. So I've labelled the key parts of it. So this is where the director lived. This was a lecture room. It's now our big library room with our exhibition in it. This was a deliberate, conscious statement of rebuilding classical revival architecture in the east of England. It's the first major building of that type. Over here here was an assistant's house, but over here were the two working rooms. So here, this slit opened up, and inside there was a mural circle. I'll show you it in a minute. And over here was the main instrument, a transit circle. Again, that opened up, and the transit circle looked out the sky. The building is exactly east-west. And this line here, a north-south line through this line, established the Cambridge meridian. In those days, each observatory had its own meridian. We're about only a mile or so off the Greenwich meridian. But we had our own meridian, and that meridian was set by moving between the middle of that slit and a lamp hanging on Grantchester Church Tower. And so every night of observing, somebody would have to go over to Grantchester Church, climb up and light the lamp on the tower, and that was how they calibrated their instruments. There's also, and even people who have worked in the building for years haven't noticed, but this is a completely false window. And everybody thinks, oh, it's got a curtain behind it, but it's not. There's a wall behind it. And so I defy you to go over. Every single person I have asked said, oh, no, it's just a window, but it isn't. It's an architectural curio designed to be symmetric with this. So the architect thought it would be nice to have a window, but of course you don't have a window opening into an observatory. It's dark at night. So anyway, that's one of the little architectural curios that carried on. The commissioning director, Robert Woodhouse, died almost immediately, as did his wife, and it's there are scurrilous stories as to how and why, and I'll leave you to go and look in our exhibition to find out a likely explanation. But these are the instruments that one had in the modern observatory of the day. This is the mural circle, so it's a telescope that moves up and down. You look through the telescope. And we have a full-sized print copy of this very instrument hanging in our exhibition. The original's now in the Science Museum. It's 8 feet across. It's a beautiful thing. Go and see the picture. The second thing you had to have in an observatory was a set of clocks. And the third thing was the transit telescope. So this was the one that you look through for the north-south route. This isn't actually the original transit circle. There's a drawing of the original one in the exhibition. This one has only slightly different coordinate circles on it. Otherwise, it's the same. And you can see the way of observing. You look through either of these telescopes. You listen to the clock ticking. And at the exact time at which the star crosses the meridian in your telescope, you note the time and you read the elevation of one of these dials. And then from that time and the elevation, the computers the next day can work out where the star is on the sky. That was 19th century astronomy. The goal, of course, was not only to improve and map stellar positions for all sorts of things, but primarily it was to improve planetary ephemerides. Where are the planets on the sky? It was known that they weren't quite working, but it wasn't known whether the problem was the data or Newton's models. And similarly for tracking comet orbits. So the whole goal was to set up reference systems on the sky and then test out Newton's laws and apply Newton's laws. And this is what they did through the whole of the 19th century with his eye and ear observing. So after the first guy died, the next and first successful director was Airy, George Airy. He was a very ambitious and professional person. So he was the Lucasian professor when he was offered the job, but he immediately resigned the Lucasian to become the Plumian because it was better paid. And then immediately in his first meeting demanded a doubling. So this was the Plumian endowment. He demanded a doubling out of university funds and got it. And then he demanded an extra, same again, to apply some people to do the work. So he was a true professional, was Airy. He was also very ambitious, so he didn't stay very long. He very quickly went off to Greenwich Observatory and did the same thing there. But you can see in this is the record of the first visit to his new observatory by the group, the members of the university and strangers, as they were charmingly called at the time, who came along to make sure that Airy was doing well. And you can see that he was doing well because he had labelled every single book. He had written every single item with a code number in the records. He had labelled all the boxes, and even he had taken empty boxes and put a label on them saying empty box. So that tells you everything you need to know about Airy. He was what in modern jargon we would call a complete nerd, but he was extremely effective and efficient at getting stuff done just because he was such a control freak. And so he got the place working. He also finished the instrumentation, which is this telescope, which is still there. This is the building's changed since, but this is the Northumberland telescope, which is still there. And John Herschel, another of this group, had persuaded the Duke of Northumberland to fund the missing big telescope for the observatory. And so Herschel basically gave a blank check to Airy, who did all the work, designed the telescope, reorganized everything. He actually set up the tensioning. If you've seen this telescope, it's a big wooden structure. He set the tensioning on the wood so well that it's still in alignment 200 years later. So he did the whole thing himself, even though by then he was back in Greenwich. He just couldn't let things go. But many of you who will have degrees from Cambridge will have walked through the Senate House lawn and will have walked past this big, huge vase in the Senate House lawn and wondered about it. And it was given at the same time by the same person, the Duke of Northumberland. And it's a model of something that was in Hadrian's Villa. For the Antipodeans visiting us this week, I just couldn't help resisting putting this here because it's a model for the Australian Open tennis trophy. But given this thing's about 2.5 meters high, I don't think it's a one-to-one model of the trophy. So after Airy left to go to Greenwich, then the next person came along, James Challis, and he was much less successful. Challis tried to do everything that Airy was doing, but he wasn't a control freak. And so he got behind with everything, struggled to keep up, tried to do more and more and more. And eventually things just drifted behind. He stayed as director for quite a long time, but things just drifted more and more behind. But the reason we remember him is not that things were behind, but for what is now known as Neptune Gate. And this is because at the time, that Neptune was discovered from anomalies in the position of Uranus, exactly what 19th century astronomy was all about, right? You set up a reference grid, you check the positions of the planets, and you found if they were a bit different, and they were. And from that, the presence of Neptune was predicted, and it's approximately placed in the sky, and it was found very quickly after Leverrier published it. But some months earlier, half a year earlier, a young student at the time, actually, John Couch Adams, had done the same calculation in his holidays and had told, well, not quite told, he'd sort of given the information to Challis and to Airy. We'll come to Adams in a minute. And eventually, after some months, Airy sort of bullied Challis into starting to going to look for this predicted planet. And so Airy started with some further help from one of Airy's assistants, and in fact had observed it several times without realizing that he'd observed it. So after it was discovered and its discovery was announced, a particularly shabby and underhand scheme was developed by Airy and Challis and a few others to claim that they'd really done it first and hadn't got around to publishing it. Their motivation being this was done from Newton's laws, and they owned Newton, right? He was a Cambridge man. No one else was allowed to use his laws better than they would. And so you can see here some of the dishonesty. It says the planet was in effect discovered when it hadn't been discovered at all. It was listed as a star, just a boring star by Challis, who had no idea what it was. But anyway, they continued this scheme for some months before backing down in cringing shame. The other things that happened during Challis's regime were, first of all, this point here from Darwin, the origin of species. Just, again, remember, this was another thing that the founder, George Peacock, did. It was George Peacock who identified Darwin as the person who should go on the Beagle. So Peacock really deserves a very great deal of credit, because origin of species is not a bad thing to have done. And secondly, the first big endowment by a woman at the time was made. Anne Sheepshanks gave a huge sum, 5 professorships equivalently, as an endowment to the observatory in 1859, and this basically set up the observatory for its future post-Challis. So post-Challis we get back to John Couch Adams, the same person who was a student, had predicted Neptune. He became Plumian Professor, so he's a mathematician. And he was a very strange person. He was incapable of communicating with almost anybody, which is why part of the confusion with the Neptune thing. He was incapable of turning up to the vast numbers of committees he was supposed to chair and so on. But he was highly regarded at the time as a mathematician. And he made one very, very smart choice, which was, I will be director only if I don't have to do any work. And so he was very, very clear, is that, okay, we've got in our trust fund, I will buy the new upgraded telescope, I will hire the best astronomer I can find, Mr. Andrew Graham, to come and use it, and I will give him some staff and I will support him. And so he set up this program, and he set the scientific goal, which was to do, by this time all of astronomy, at least Western European astronomy, was getting organised, and they carved up the sky and decided that rather than doing random bits of the sky, they would be coordinated. And so this was called the AG catalogue, after the German Astronomical Society. Cambridge got its own. Adam signed up to it, said, okay guys, go to it, I'll support you, whatever you want to do. And so things went on rather smoothly then for 30 years or so, until eventually Adams died. And the new person came in, Robert Ball, again another Lowndean. He had been a prominent mathematician earlier in his career, though he'd given that up by now. The first interesting thing about him is that he was prepared to come at a half salary, provided that there was a house extension for his 6 children. And that's where the big 2-storey brick extension on the east end of the observatory came from. It was the Ball children's salary. He also did one other little thing, which is unfortunately I can't find, in that Robert Ball famously built a time ball. So we have the ball, but I cannot find the ball, but I'm sure it was a fun thing to have at the time. But anyway, his site was going. He wasn't interested in doing any observing, but he set up a program. He was very much like Adams in the sense where he said, right, I'm hands off, but I want to modernise the system. It's been 35 years, time for a change. And so he, as we'll see in the next slide, he built a special telescope which was designed for the new technology. The new technology was photography. And the scientific challenge then was parallaxes. They'd gone beyond positions and were starting to do parallaxes. He set up a new set of staff with a rather brutal transition, which you'll hear more about shortly. But his total interest was, apart from teaching, which apparently he was very good at, teaching the undergraduates, his total interest was popular books and public lectures. He claims to have given 2,500 public lectures. And his popular books were enormously successful. So he was a very, very successful public figure, but didn't do anything with the observatory except lead people to it. But this telescope, the Sheepshanks telescope, turned out to be a triumph because the work on stellar parallaxes was taken over by a young visitor, H.N.R. Russell, together with the local staff who was employed to it, named Hinks. And Russell had just finished a PhD in Princeton and been sent by his family to King's College, actually, to Cambridge, to recover. He wasn't well. And they said, go and get away from all the stresses of Princeton and go to a nice place like Cambridge and enjoy the wine cellar and whatever. And that worked. Russell very quickly recovered and got bored. And after a few months, he came along to the observatory and said, you know, I've done some astronomy. Is there anything I can do? Find me a job. They immediately realised they had a treasure on their hands, and Ball, with some help from other Cambridge supporters, got some money from the brand new Carnegie Institution. And that funded Russell to stay for another 2.5 years. And so Russell then worked on stellar parallaxes, while Hinks split his time between stellar parallaxes and a second parallax project, which was called Solar Parallax. It was actually determining very accurate orbit of the newly discovered minor planet Eros to determine the scale of the solar system. But anyway, the Russell work turned out to be quite successful. This is the Sheepshanks telescope. You can see a movie of Eddington opening the roof, or closing the roof actually, of the Sheepshanks telescope over in our exhibition. But it was a funny looking thing, but it worked very well and worked very well for photographic parallaxes. And so, as described in this great famous article by Henry Norris Russell and Arthur Hinks, that they did half the work each. Russell then went back to the US, got the rest of the data he needed from Mrs. Fleming, and created the Hertzsprung-Russell diagram. Undoubtedly, bar none, the great advance in stellar science at the turn of the century. So this was after the reform of the mathematics curriculum. This is the second great triumph of the Cambridge Observatory, although almost nobody realises that the Hertzsprung-Russell diagram was done here in Cambridge. It was. and the whole of 20th century stellar astrophysics depends on that, and we still depend on it to this day, and it happened just over there. Now, I'll hand over to Gudrun, who will now tell you some of the, about some of the people who were involved in this at that time.
Okay, so I'll take you briefly interrupt the flow of history and take you to just under 50 years at the observatory, and talk about the women associated with the observatory during this time. Starting in 1876, which is the time when the first woman was employed at the observatory, and ending in 1923, when the two ladies at the bottom of the slide left the observatory, much inspired by the observatory, and went on to do great things elsewhere. 1923, we have to bear in mind that we're still 25 years away from the time when the University of Cambridge gave women full membership of the university, and therefore the right to take degrees. So I will start with the woman about whom not much is known. So much so, really, that we don't even have a picture of her. The information that I will share with you is based largely on the research done by my colleague, Mark Hearn, and a colleague of his, and I refer to their forthcoming publication here at the bottom of the slide. Annie Walker wasn't the first woman employed at the observatory. That was Harriet Hardy, who was engaged from 1876 to 1881 as a clerk calculator. And employing women at the time was an initiative by the then director, John Couch Adams, in response to the need for more staff because of the observing program. But it also responded to economic pressures because women came at half the price of men. And so really being cheap became an opportunity for employment. Annie Walker joined the observatory age 15, really as a schoolgirl, part-time at first, having distinguished herself in mathematics at the local junior examinations. When Miss Hardy left, Annie Walker joined full-time and then worked at the observatory for a total of 24 years. Initially, she was employed and engaged as a calculator, but she very soon developed great skills as an observer. And ended up doing an enormous amount of observing for the observatory, and her work was much admired and much praised by her colleagues, among which Andrew Graham, himself a very experienced observer and therefore able to assess Miss Walker's talents. She had the opportunity to develop these skills because she was living on the premises. She was living in the observatory. She had a room with Andrew Graham and his wife, and that meant that she could do nighttime observing safely. Andrew Graham was also at the time getting quite old, so it gave Annie Walker the opportunity to stand in for him. And Henry Todd, the second assistant, wasn't in very good health, and therefore, again, Annie Walker stood in for him and had the opportunity to do much more observing, and also observing on her own. Given that she was paid to do all this work, even though she was never really properly engaged as an observer, it's fair to say that she qualifies as Britain's second woman professional astronomer after Caroline Herschel. But Annie made no discoveries, she didn't receive any public recognition, and we don't have any picture of her. And her position in the observatory remained anomalous. So here are the observatory records, and we see Miss Hardy in 1880, the first woman employed. Miss Walker appears from 1882, and from the first time she appears, it's already noted that she bids fair to become a good observer. John Couch Adams' initiative was noted and publicized in the English Women's Review of 1883, which draws completely on the observatory records, and again notes Miss Walker's abilities and the prospect for good observing. And over the next decades, Miss Walker's contribution to the work of the observatory are duly reported in the observatory records, and her skills and expertise noted by her colleagues. We have seen this picture before. This is the instrument on which Annie would have worked most of the time. The person in the picture here observing is Andrew Graham. Of note is here the entry of 1891, which is the last year of John Couch Adams' directorship before he dies. And we see here how much appreciation he shows to his staff and the praise he gives to them as a team for having worked so skillfully, and that includes Miss Walker, to progress the work which was so important in the observatory, which was the zone catalogue observations. In 1892, things changed slightly with the arrival of a new director. Robert Ball has different priorities, and the first thing he does is to retire the second assistant, Mr. Todd. He doesn't fill the position. He doesn't offer the position to Miss Walker. On the contrary, she's not allowed to apply for it. Instead, he appoints Mr. Morris just as a member of staff to help out, because he has already his sights set on his ideal candidate, who is a young graduate from Trinity College, Arthur Hinks, who will be offered the position of second assistant even before passing his examination, his Stripers examination, and it's despite the fact that by Hinks's own admission, he's not even a particularly good mathematician by Cambridge standards. In 1897, the zone work, the work on the zone catalogue is completed, and this is really where Miss Walker is effectively thanked for her work for the observatory. She is praised for her industry and painstaking care, but from now on, any work that she does, and she will continue to do observing for an enlarged version of the zone catalogue, and also new work, which is referred to once here. From now on, her work is really relegated to the back and no longer considered important. From 1900 onwards, there's no mention anymore of Annie Walker. In 1902, two new members of staff arrived. They're two students, female students from Girton College, who are employed to work on Mr. Hinks's solar parallax project. We will hear a little bit more about Julia Bell, who is one of the two students. Again, the reason for employing women is because they were cheaper than their male counterparts. So it became clear from 1903 on, soon it becomes clear to Annie Walker there will be no room in the observatory for her going forward, and literally so when Andrew Graham retires, aged 88, Annie Walker loses her precious accommodation as well and has no other option but to resign her position. She has nowhere to go. Her family has emigrated to Australia, so that's what she does. She goes to Australia as well and joins them. And sadly, there is absolutely no evidence that she was ever able to resume a career as doing observing or doing astronomy. After she leaves, Mr. Hinks is promoted to chief assistant, and a new graduate, male graduate from Trinity College is appointed to the position of second assistant. It's amusing that about 10 years later, Mr. Hinks ends up having a bit of a Miss Walker experience, since he is then passed over for the position of the directorship, which will go to Eddington. When he arrives in 1914, his first task is to tidy up some of the uncompleted observing work, and he will even do some of the observing himself. And doing so, he will see to it that the remaining observations made by Annie Walker are published. And that will become an appendix with revision observation made by Miss Walker, which is now really, this will be published in 1919, effectively a publication for Miss Walker. He also gives her full credit, including for the fact that she was, from 1894, the sole observer for much of the observing that she did. And so there's a full record and recognition of Annie Walker's work as an observer by Eddington. There's no reason to believe that Eddington did that to give recognition to a woman. Eddington's focus would have been on making sure that the scientific information was correct and complete, and that would have included the identity of the observer regardless of their gender. Before looking a bit more at Eddington's directorship, let's look at Julia Bell, who we met earlier when she was appointed as one of the computers on Mr. Hinks's project. Julia Bell worked for the observatory for 6 years on the project, mainly remotely, it seems. And on the basis of her work, she was able to receive an MA from Trinity College Dublin. That was because, again, neither Oxford nor Cambridge were awarding degrees to women, but there was a scheme in place for a couple of years which enabled Oxford and Cambridge women to receive an equivalent degree from Trinity College Dublin. And because these women sailed to Ireland, they were called steamboat ladies, and Julia Bell took advantage of this opportunity. She then resigns and from 1908 becomes a statistician working as an assistant to Carl Pearson. She then develops an extremely successful career as a statistician and geneticist, much encouraged by and supported by Carl Pearson, who encourages her to take a medical degree, which she completes in 1920. She had an extremely long and successful career, only retired in her 80s, lived to 100. And I think on the basis of the career that she had, it's safe to say that she probably contributed very significantly to the work that she did at the observatory for Mr. Hinks. And it's quite amusing that her own recollection is that she mentions is that the physicists of the day were not mathematicians and were unable to see the truth. And now to the arguably two most famous women, Cecilia Payne and Alice or Ali Viber Douglas. The reason they are on the same slide is because to make clear that they were both not only in the same college, but they actually overlapped in Cambridge. They both really benefited from their time at the observatory and then went on both to do at first astrophysics PhDs elsewhere. Cecilia Payne came to Cambridge in 1919, initially enrolled to do botany as part of her degree, which she soon abandons because she finds physics much more interesting. But it is a lecture that she attends by Eddington in 1919 about the eclipse results that verified Einstein's theory of relativity, which convinces her that it is really astronomy that she wants to do. And I think it's fair to say that as well as extremely talented, Cecilia Payne was also extremely determined. And once she decided that astronomy was going to be what she wanted to do, she said she did what she needed to do to achieve that. She wasn't formally able to do astronomy because that was at the time still linked to the mathematical tripos. But she then set out to attend the lectures that she needed to attend and get to know the right people, and also read all the books that were available to her. And she achieved great success, as we know. Ali Viber Douglas was a Canadian lady, very interested in science from an early age. She says she was very frustrated as a young girl that she couldn't attend things like a science club because she was a girl, reliant on her brother to leave the door open to the room so she could sit outside and listen to the information nonetheless. She studied sciences but interrupted her degree during the war to come to Britain, and where she worked as a statistician in the London War Office. And for that work, she received an OBE in 1918 from King George V. She then returned to McGill and received a degree, followed by an MA, and then obtained a scholarship to study under Rutherford and Eddington. And so this is where the two women will inevitably have met, and it is quite likely that they were sitting together in perhaps at least some of the lectures given by Rutherford, and they were certainly together as research students of Eddington, as we'll find out in a minute. It's quite amusing, therefore, that neither woman chooses to refer to the other one in any of the further literature. So here they are in the observatory records. These are among the 4 research students that Eddington mentions in the records, and it's quite amazing that there are 50% women among Eddington's research students. The other 2 are William Greaves and Leslie Cumry, who went on to become very distinguished in their own right. And it is, in fact, it's Cumry who he was in 1922 about to go to the US himself for his own career. But it's Cumry who introduced Cecilia Payne to the director of the Harvard Observatory, Harlow Shapley, and enabled her to tell Harlow Shapley that she really wanted to go and work under him, which she then realizes. And Harlow Shapley became Cecilia Payne's supervisor for the groundbreaking work that she did in her PhD thesis. The entry of 1922-23 shows the 2 women in relation to publications that they both made with or through Eddington. So Ali Vibert Douglas co-wrote a paper with Eddington, and Eddington encouraged Cecilia Payne to write up research results and publish them. And that effectively became her first publication in Cambridge. So it's fair to say that both women were much encouraged by their time in Cambridge and went on to do first astrophysics PhDs elsewhere. So summarizing, we've seen that in times that were extremely challenging for women, we have seen 4 women who nonetheless managed to have careers. Annie Walker, admittedly only half a career at the observatory, but the other 3 women, on leaving the observatory, achieved significant careers. And that was obviously due to the fact that they were extremely talented, hardworking, and also very determined to do what they wanted to do rather than what society was perhaps expecting them to do. But almost as importantly, we have also seen that all these women would have been reliant on the people who were in a position to provide support or withdraw the support. And in those times, there would have been, they would have all been men. And it really depended on where the focus of all of these men was lying. Of all of them, I think Arthur Eddington comes out on top. And he famously could segregate completely between what was important from a scientific point of view and what was relevant from a more personal or individual point of view. But it's also clear that Eddington, in spite of his position, in spite of his distinction, wouldn't have been able to find room in the observatory for Cecilia Payne's research. It just wasn't possible in those times. And so before I hand back over to Jerry, we'll have the opportunity now to listen to Arthur Eddington describing the breakthrough discoveries made by Cecilia Payne.
Firstly, that ammonia and methane are compounds of hydrogen, and they are the gases which we should expect to find in a world where hydrogen was plentiful, because hydrogen is an active element which eagerly combines to form such compounds. Secondly, hydrogen is very plentiful, nearly everywhere in the universe. This is one of the most important astronomical discoveries of the last 10 years. We had not realized before that outside the Earth, nearly everything is simply soaked with hydrogen. And it helps us to understand a lot of things that were previously very puzzling. By various methods, it is found that in the sun and stars, not only on the surface, but in the deep interior, there is more hydrogen than all the other elements put together. So Jupiter and Saturn agree with the general rule, and the Earth is the exception, exceptional in its shortage of hydrogen.
Well, we believe that's the first time Eddington's voice has been heard in 80 years. As this recording was discovered only very recently indeed. However, I will now move on and look at how astrophysics came to Cambridge. And astrophysics covers this part of the site. So to orient you, the field is out there. And there's quite a lot of it, but the history of it's interesting and complicated. So first is, what is the astrophysics that came to Cambridge? Well, there was a lot of astrophysics in London, but in England at the time. Starting in the 1860s, the two great pioneers, William and Margaret Huggins, had pioneered astronomical spectroscopy. They just invented everything that you've ever heard of. They did photographic stellar classification, radial velocities, quantitative analyses. They were the first to realize that what previously had been called nebulae were actually a variety of astrophysical different things, some emission, some absorption lines, and so on. And they were great, truly great pioneers. Their observatory, their telescopes, were funded by the Royal Society, and when they retired, by agreement, they moved the whole thing here to Cambridge with a nice bronze plaque, which we still have. And the statement was that it was moved to Newell's Observatory. It came to join Newell's telescope. A new dome and a building were required and were funded by Newell. The other observatory, other astrophysical observatory in England at the time, was not far away, also on the site of what is now Imperial College. And this was Norman Lockyer, who was also another very impressive astrophysicist. He discovered, as you see, the solar chromosphere. He independently discovered helium, in fact did it first. But when Imperial needed the site, he was long retired. It was a government-funded thing, so it needed to be moved. And this was a perfect opportunity for Cambridge to set up a stitch-up. So because committees were needed and because Cambridge knew about the thing, first of all, the university, i.e. Rayleigh, decided that they had to show they were serious. So they created the 1909 Astrophysics Chair, and that's where that 1909 Astrophysics Chair comes from. The holder of it is sitting here. It was possible only because Newell was very wealthy and took no salary. So they created an unfunded chair, but they had the title. Then over the next 3 years, a whole series of committees were set up to independently review the best possible future for Lockyer's observatory, and magically they eventually ended up with 4 Cambridge men recommending Cambridge. Just in case they needed to justify their decision, they got some independent advice from George Hale, the great American observatory builder and solar astronomer, and he generously agreed to agree the text of his advice with Joe Larmor before he provided it. So here was a lovely example of a committee coming to a preconceived decision with appropriate interpretation of the evidence. Completely impossible to imagine that happening now. So what happened then, of course, not surprisingly, is the whole thing moved to the already available Huggins Observatory and merged to create the new Solar Physics Observatory on the 1st of April, an appropriate date, 1913. But there was an interesting new condition added at the last minute from Lockyer in an attempt to muddy the waters. He said, but meteorological observing is really important. And so the university agreed that they would create the post of meteorological observer, and they appointed a young person, C.T.R. Wilson, whose job it was to prepare laboratory experiments in the Cavendish. And so this was the takeover of astrophysics. It all moved to Cambridge. So who is this Newell that we're talking about? Hugh Frank Newell, the original 1909 professor of astrophysics. He had a ridiculously wealthy father, R.S. Newell, and this was the hobby telescope of his father, who invented the transatlantic telephone cables, actually. So it had a hugely rich and successful thing. And this telescope's now in Athens, and there it is with me looking through it. Here is Newell and his wife. They had no children, so they needed a small cottage on the site, and here is the cottage that they built. It's just over the driveway there, 100 metres away, and it later became Earth Sciences, and it's still there, of course. It's part of the Earth Sciences lab. And where the telescope was is now the Kavli building, and this plaque just out, which has its own story, I don't have time to tell you about it. This plaque just is where it went. But Newell, who was an enormously generous benefactor, he spent his whole adult life working here at the observatory, never took a salary, quite the reverse. He funded absolutely everything because he was very wealthy. And as summarised by Milne in his obituary, he said his life's work was building up and establishing astrophysics. So he wasn't a research scientist in his own right, but he was a brilliant administrator and a very generous benefactor, and so he created astrophysics on this site. There was one interesting bit of the astrophysics, and that was this last-minute add-on of the meteorological observer, C.T.R. Wilson, who turned out to be quite a good find, actually. Because Wilson was interested in weather, thunderstorms, and atmospheric electricity. And so he developed what he called the cloud chamber to study the clouds. Here is the cloud chamber. There is a replica of it in our exhibition in the library that you can go and see. It's the exact replica. The original is a bit fragile. But you can see what Wilson was doing from the first years over here. He's not only studying thunderstorms, but he said, oh, by the way, I can also study X-rays and beta rays. And this, in fact, was the beginning of nuclear physics. So Wilson's cloud chamber was the tool which was used to develop nuclear physics and the whole physics of X-rays, beta rays, alpha rays, and what they were, and so on, in years to come. And in fact, there's a giant cloud chamber model, much bigger than that one, still at CERN. If you ever go to CERN, it was the first detector they ever had at CERN in Geneva. So this dominated physics for half a century, and so he deservedly got a Nobel in 1927. And that all happened out in our lawn. I mean, nobody knows, but it worked. He worked in this little shed there. That was where the Nobel Prize was won. But there's no blue plaque on it. But there was another interesting thing. These other bits and pieces on this lawn over here were atmospheric electricity studies, studying the newly interesting ionosphere with Appleton and Ratcliffe, the great names of the subject. And all this happened there. So in this little tiny dome was actually a radio transmitter dome. And there was another radio transmitter next to the cloud chamber there, and another one in there next to that heliostat. So this add-on to solar physics not only led to very substantial physics of the ionosphere and radio science, but also to the cloud chamber and a Nobel. Again, like the HR diagram by anybody's standards, this was spectacular science. And again, nobody seems to realise that it actually was here. It was part of the observatory. It's part of our history. The other part of our history is less easy to make much fuss about. The solar physics went on for a long time. After Newell, the lead was Stratton. They spent a lot of time on eclipses while he was there, and after him there's this guy, Harold von Kluber, who came in 1948. He'd been director of Potsdam Observatory in Berlin during the war, and he came over and stayed here for the rest of his career. And eventually they moved the solar activities funded by Newell in that dome just over there to Malta. And there it is. That was the Cambridge Solar Telescope on Malta, and here's the castle in which von Kluber lived for a few years before it was all shut down. So they did useful work, but nothing that with hindsight has left anything like the impact of the Nobel laureate next door. So now let's go back to the observatory and see what was happening there in parallel with this. So we're now back with the Sheepshanks telescope left from Ball, the Northumberland. The Newell was part of the astrophysics. It wasn't part of the observatory. And the observatory again. And a rather interesting thing happened in 1914 in that they ran out of money, they wanted to do something, they had to worry about funding a chair. The Plumian electors decided that this bright young bloke, Eddington, might be useful because he could do both observations and possibly a little bit of theory. But they didn't have any money, and so Newell therefore fully endowed his 1909 Astrophysics Chair and guaranteed that he would take no salary ever. And so this freed up the money for the university to appoint Eddington. Hinks had just had a ball done to him, and so he resigned and left astronomy, having not been considered adequate for a promotion. And he disappeared after that, went into management. But Eddington, as you just heard, for his first few years, he actually did the observing. He actually went out and did the eye and ear observing through the transit telescope, tied it all up, polished it off. He did one more set of observations, and then that was the end of it. And that, of course, was the famous 1919 eclipse expedition, which was sort of a grand finale to go out on. I think most people would consider that something pretty spectacular. And so all in all, he did turn out to be quite a good choice. But he did everything else as well. You name it, he did it. Those of us who are at the conference today will have noticed that Eddington's name keeps popping up on slides. It's the most quoted name in this conference. And I checked a couple of hours ago, and so far this year, in the astronomical literature, Eddington's name has been quoted more than 2,000 times. This is 100 years later, okay? We're still getting quoted 4,000 times a year. So he clearly was quite a good guy to have around, actually. It was a good choice. He was also a bit complicated, but was universally admired, as you see this biography, a biography by Eddington, the most distinguished astrophysicist of his time. But he was a complicated person, but because of all this stuff, he was on such a high pedestal that later on people started trying to shoot him down. And in the 1980s, it became fashionable to say that, oh, Eddington, here he is with Einstein sitting outside the building there after his this was 20 years later. Einstein only came to Cambridge once. He went to Oxford a lot. But so in the 1980s, it became trendy to say that Eddington's data was so poor quality that he actually cheated to prove Einstein's equations were verified by experiment. And so therefore Eddington was dishonest and dishonourable. And this went viral through the internet, and you'll find everywhere that Eddington was a cheat and Eddington debased science and so on. So Gudrun and I decided we're going to have a look. So we went back and looked at all this 1980s and later literature, redid all the calculations and checked everything, and discovered that actually the people in the 1980s messed up their maths and got it wrong. They just had been second rate at statistics, and that Eddington actually had done the right thing to the limits of the statistical knowledge of the time. And so Eddington survives this attack on his integrity as a man of the highest possible integrity. He was nonetheless a complicated person. I could give many, many examples of this because he was famous for the way he would be negative in debate about people. So there's that charming debate in Green, not a debate, a comment in Green about a paper by Milne. Now Milne was a colleague of Eddington's, right? Milne had been here with him for 7 years. They knew each other really well. And yet he would say something like that. And I could have given you 5 other people that he said similar things about. He with Jeans, they were the astronomical community would famously go along to the Royal Astronomical Society every the monthly Friday meeting for broadswords at 3 paces, as it was once described, with Eddington attacking everybody. But nonetheless, he somehow did this, as Gudrun pointed out, by distinguishing between the individual and the science. He attacked the science but not the people. And everybody liked him. You can see what Milne said about him in spite of that and many other things. He truly was a great man. However, my next slide will show that Eddington founded what is now a famous Cambridge tradition of Plumian professors going very, very odd indeed. And he spent the last quarter of his working life working on his theory of E-numbers, which no one has ever understood a word of and was complete nonsense, but he took very seriously, and he took it so seriously that it led to this famous issue, the Chandrasekhar-Eddington dispute. This is, again, it's in our library. This is our bronze of Chandra, who was here. And you probably already know the story. After Chandra, as a young man, discovered the Chandrasekhar limit, the maximum mass that a star could have as a white dwarf before collapsing to something, which we later now know as a neutron star. Eddington said this must be nonsense and attacked the science repeatedly, but without ever disagreeing with the equations. He could never ever find anything wrong. No one ever could, of course, because it wasn't with what Chandra did. But well, it became clear even at the time is why he was so insistent about this negativism, about relativistic degeneracy, because as he fully understood immediately that the entirety of his fundamental theory depended on relativistic degeneracy not being correct. And so as soon as Chandra came along, this totally undermined a third of Eddington's life's work. And he found that hard to accept. But you can see it was Chandra who said the greatest physicist, astrophysicist of all his age. He's always operated with preconceived ideas. So he somehow, it wasn't a personal attack, but it wasn't a nice thing at all. I noticed, just as in passing before we move on, that here is the reference to Chandra having come as a student. And there was also another Indian, V.V. Nalakar, also here at the same time. This V.V. Nalakar later became a prominent proponent of general relativity, having been taught by Eddington back in India. But perhaps more interestingly for present stories, he's the father of giant Nalakar, who later came to Cambridge and is the Nalakar who worked with Fred Hoyle and was one of the foundation members of the Institute of Theoretical Astronomy. So there was that two-generational connection carried on there. Now, so clearly we've had another of those triumphant moments. Eddington was another triumph in the history of the observatory. So now we'll move on to what came next. And what came next was that they got rid of all this stuff. So it was the termination of the Solar Physics Observatory. So all of the solar physics things were removed. This was in 1950, after the war, they got rid of everything. This, in case I forgot to point it out before, is the dome for the Huggins telescope that was built by Newell, and this was then a house and an observatory was the Solar Physics Observatory. So that was all removed. Just while Eddington was still alive, they reorganised the administration, moved the observatory into maths. After he died at the end of the war, they moved the observatory back out of maths, but they left the Plumian Chair behind, so the Plumian Chair was removed from astronomy at that time. They created up a new merged observatory under the Astrophysics Chair, and this was essentially the termination of the Cambridge Observatory. They shut it down. It just became what it is now, a library and an office building. Some observational astronomy continued with a slow growth in numbers, with a big focus on solar observations, which then moved to Malta. But at that stage, Cambridge's astronomy wasn't leading what was going on in the world. Down here is my little summary list of all of the other things that were happening through the 60s, 50s and 60s. And it's a long list of really exciting things. And it wasn't happening here. It was happening a lot of it was happening in applied maths, but it wasn't happening here. And so what happened then, of course, is that applied maths was the place where all the interesting new astrophysics was happening. So Fred Hoyle set up his Institute of Theoretical Astronomy, and here is the building. We're in the end of this thing. And that's what it turned into today. So here, this part is the Institute of Astronomy building, and this is the computer centre, which is so important. And there's these other things I'll come to very briefly. So now, just my last two slides, just quickly. The IOTA, it was triumphant success, of course. Why? Well, because it was absolutely cutting edge, and it was precisely timed to capitalize on all of the big changes in society and science in the 1960s. So first, there was a lot of money around. Secondly, an awful lot of stuff had been declassified, and so nuclear astrophysics and cosmology and relativistic astrophysics was developing. APM here had the third biggest computer in the UK, in that little building just out there. They had a fantastic summer visitor program, and here you see the original members of IOTA, half over from other places, and the rest bright young people. Many of these names later became very famous. But you can also see how many people it took to run a computer in those days. But the other feature of IOTA, of course, is that Fred did all this through the strength of his personality. But because of the strength of his personality, he also became a single point weakness because he wasn't prepared to compromise on anything. And later on, with Nalakar and others, he continued this Cambridge tradition of going very odd indeed and working on all sorts of strange things. But the IOTA he created was triumphant, and it was so successful that the university claimed it was merging it into a new Institute of Astronomy. In fact, the IOTA was a complete reverse takeover. So the Institute of Astronomy was an expanded IOTA, and the Solar Physics Observatory and Astrophysics was all just simply completely literally shut down. And so all of the IOA was just a big IOTA. It was led by the Astrophysics, the 1909, which was Donald Lyndon Bell, who's over here. That's what he used to look like. And this was the remit from the university, which was written by Fred, of course, and so he was right. He said, okay, we don't want any more second-rate stuff. Let's go and use the best telescopes in the biggest places. And in fact, the Anglo-Australian telescope was being built at that time, and next month is the 50th anniversary of the dedication of the Anglo-Australian telescope, which was done by the young Prince Charles. And Uhuru is the name of one of the first X-ray satellites, so space science was coming up. So everything was changing. So the idea was that people would then go to the best facilities on the planet and come back to the best computing and the best minds and do the analysis here. Fred resigned for reasons that you can read about in his autobiography or on the St. John's website, or you can ask there are several people here who know, ask them. And Martin Rees was appointed. Now here is a young Martin Rees. You see, unlike Donald, who always wore very conservative ties, Martin has a penchant for rather more colourful ties, but other than that, he also has more hair. But what happened literally was the next 25 years, IOA was a big IOTA, and it was a triumph. There's no other word for it at all. The summer science program, the computing, the students and the postdocs, and the very rapid growth in astronomy just made this the place to be. And oops. I was one of the people lucky enough to be here at that time, as many others in the audience were. And it was a world-leading, world-class thing under Martin and Donald, and was great. But nothing lasts forever, and after about a quarter of a century, there was so much money going into astronomy, and so many new, brilliant students and postdocs had been here, they went back to their own homes and they created competitive institutions. And so suddenly there was astronomy everywhere. And Cambridge was no longer that special. It was, well, still quite good, but it was not that special. And over the last, you can see my last point here, over the last decade or so, 2 decades, the real change has been the growth of mini IOTAs through things like the Kavli Institutes and bringing the Peacock sitting next to us so that we can actually be part of multi-wavelength, multi-messenger science and so on. So perhaps we're rebuilding the IOTA expertise, but I won't say any more about the recent past except to emphasise that the first 25 years of the last 50, which is the bit that's far enough away that we can actually start to talk about, was a triumph. And just to remember that in all this stuff we're talking about, the past was a foreign country and they did things differently there. Thank you.
Wonderful. Thank you, Jerry and Gudrun. Thank you so much. You know, I worked in the Obs building for years. I had no idea that was a fake window. You're blowing my mind. Do we have any questions for either of our speakers? Kathy?
What do you know about Anne Sheepshanks?
Oh, okay. Yeah, so she was, by the standards of the time, she was an outstandingly independent, wonderful, amazing woman. Her family, she was unmarried. Her brother was a prominent astronomer who was very enthusiastic about lots of things, managed to get himself into astonishingly bitter arguments with everybody involved, realised that the challenge for an observatory was professional staff, tried to get this set up through the university and same thing through the Greenwich Observatory and failed, then died. And so his sister appreciated the argument. She was also interested in astronomy. They were wealthy people, none of them ever worked. And so she gave this very generous donation in memory of her brother, but it was her money and she gave it to the observatory and so she, as Anne Sheepshanks, was, I believe, the most generous English woman donor of the time. There are a couple of similar ones in the US around that time, but I believe she was the real pathfinder, certainly in the sciences. There may have been something in the arts, I'm not sure. Quite remarkable woman.
Question from Robin.
By my calculation, isn't it? Okay, I better speak down. By my calculation, Annie Walker was 37 when quit.
This one's supposed to be off, but it seems unhappy. I don't know.
Okay, she was 37 when she quit here, and she went to Australia. Do we know absolutely nothing about what became of her after that?
I think we know that there are a few details that are known, and so I'll just refer you to Mark's forthcoming publication. So but really relatively very little is known. I think Mark's trying to find out whether there are any records at all of any work that she's done, but it seems that she just joined her family and couldn't really do anything else.
Seems a bit sad.
Yes, I agree.
Am I right that I think I remember reading she gave her profession as astronomer for the rest of her life, is that right? So I think there was some census towards the end of her life and she, under her job she called herself an astronomer.
Yes, she did call herself astronomer in the census, that's right, but she didn't actually, we haven't been able to find any evidence that she ever was able to resume astronomy or observing as a profession after Cambridge.
Yes, please.
Terry, since you've done some work on the Eddington experiment, were the original plates or photographs ever found? I remember there was a time when it was believed that it ended up in St. Andrews.
Yeah, so first let me say I forgot to mention that giant Nalakar founded IUCAA, which became a spectacularly successful institution in India and has later on had some rather impressive directors as well. Well done, Shomak. But no, so the answer to the Eddington plates is that there was a big plate archive in Cambridge, of course, but it seems and Eddington didn't keep very many records, but it does seem that he didn't think it mattered anymore to keep the plates, because the measurements, he published every single measurement of every single star in every possible way. And he used the rather fancy plate measuring machine, the same one that H.N. Russell had used for the Hertzsprung-Russell diagram, and they knew that was absolutely state-of-the-art. And so there was no value in the plates. And he was the sort of person who didn't keep stuff like that. So it's probable that the plates were put in the local archive. There was then a rumour that a person named Finlay Freundlich from Potsdam, a collaborator of Einstein and the collaborator of the same von Kluber, who came here, wanted to remeasure the plates because von Kluber had, although a collaborator of Einstein, had become persuaded that light bending gave the wrong answer and that he wanted to remeasure them. So we checked with the people in St Andrews And they very generously went through their records and archives and so on and said there's no evidence that these plates ever got to St Andrews. And even if they had, there's no evidence they had a measuring machine capable of using them. And so the St Andrews rumour is probably just the fact that Finlay Freundlich, the man in St Andrews, had also tried to, well, he did, in fact, reanalyse the Eddington data. He reanalyzed the data from every single eclipse and magically got it precisely the answer that he wanted, which was 50% more than Einstein for every single thing. There's another whole lecture that Gudrun and I give, actually, on the dodgy statistics and interesting stories about the accuracy of those measurements, but that's for another day.
Any final questions? Okay, well, if not, can we thank both our speakers again?